Hi, everyone. My name is Mayank Kejriwal, and I'm a research assistant professor at the University of Southern California. I apologize for not being there live with you, but I am delighted to be recording this presentation on using Fodor's theory of modularity for situating large language models within a larger AGI, or artificial general intelligence architecture. So let me begin by just saying a little bit about our group and the research that we do. So we're basically an artificial intelligence group, and most of my research is in AI. So I'm not neuroscience or cognitive science, but we have started doing a lot of research at the intersection of cognitive science and AI. And as you might imagine, part of our motivation is really the amazing progress that we have seen in the AI community, for example, through the large language models. And so two of my projects, which are funded by DARPA, are related to sort of the general cognitive abilities of some of these models. So one of them seeks to ask if LLMs and other such complex models have common sense. And if not, which is kind of what we believe, that they don't have common sense, how do we develop models that can have common sense? And then the other one, which is this project called GNOME, is to build models that can react to novelty. So if an unexpected event happens, how do we get the AI to actually react without having to retrain over many millions of samples? So what is common to these two projects is that we do believe that we need to look to communities like neuroscience and cognitive science, both to understand what the models are doing, but also to then improve the models. And so that's really my interest in this, and why I was really excited to submit an abstract to this symposium. So let me jump right in and maybe say something about AGI. So this used to be a very science fiction kind of term, within the academic AI community. We did not use AGI. And even today, we tend not to use this phrase AGI when we write papers. When we do, we have to be careful, as I'll just show in a slide or two, or we risk being panned by our fellow researchers. So, the basic definition of AI, as we all know, is that it's really the machine ability to understand, learn, and act on information and events designed to augment, provide assistance to, or perform tasks independently from humans. That's a little bit of a, complicated definition. But when we think about ANI, narrow intelligence, AGI, and ASI, super intelligence, the idea really is that, ANI is kind of your AI of the past, in a way that, is, you have an AI that can play a game, you have an AI that can do face recognition, an AI that can recommend movies, and so on. But you have like one AI trained for individual tasks. Then you have AGI. This is kind of what we are working towards, and what we really believe can become possible because of large language models. Originally, the prediction was that maybe it will be there by 2040, but this was pre-ChatGPT. So now I'm hearing a lot of people say that by 2030 it could very well arrive, maybe even sooner. And we're starting to see hints of it. And then you have ASI, which is kind of the singularity, and you have this all these fears that we now have, that the AI can pose an existential threat and will even achieve consciousness, which I know is of great interest in this community. I mean, all of that is ASI. Again, used to be a very science fiction, speculative kind of conversation, but is becoming much more real, much more, in the here and now, that we feel we should start talking about it. So these are exciting times really for the community. And there are many questions around AGI, which is really our interest, which is, how do we get an AI that is human-like, that can do many different things, at least at human level? And so, but that is kind of unsatisfactory, right? So the questions that we really have are, well, what really are the milestones here? What do we need the AI to do? And how do we know that an AI has achieved AGI? How do we know that ChatGPT has or doesn't have AGI? We don't want this to be subjective. We really want, predefined objective tests. that we can use to make that determination. And so, of course, that leads us to the big question: do large language models have AGI or sparks of AGI? And there was this paper from some pretty famous authors who seem to claim that the GPT-4 has sparks of AGI, but a lot of people actually ended up criticizing this paper and felt that the tests for AGI and the spark of AGI was pretty shallow, actually, and that in fact these large language models, they may achieve AGI, but they're not there yet. And you kind of see that conversation reflected a little bit when people ask, well, is ChatGPT conscious? Is ChatGPT sentient? And for similar reasons that many believe it's not sentient, and maybe others do. The topic of AGI is similarly situated. We feel like there are hints of AGI, but we don't know if it really has it. We don't know how to test for it. There are lots of interesting questions. The answer is not obvious, is I think what I'm trying to convey with respect to these models. So by definition, AGI is equated with human-like ability, and hence we argue that we need to look to cognitive science for answers to some of these questions. And although consciousness is a controversial topic in AI, at least, it could be argued that AGI and consciousness are methodologically similar, that there are similar questions around both topics. How do we measure it? What does it mean? And I think one reason is that almost everyone, to my knowledge, if not everyone, agrees that humans are conscious and humans do have general intelligence. And so in an artificial setting, right, we are really talking about two abilities that seem to be very, I don't want to say unique, but certainly human-like. The humans are at the center of both questions. And so we do believe that there are methodological similarities in investigating the two scientifically in LLMs. And it's really, the world is open to us in doing such investigation. It's still very early days. However, we also believe that it's important not to take the analogy too far, because ultimately a neural network is not the same as a brain. It's inspired by the brain, but it's not the same as a brain. The analogy really stops there. It's really not like neurons firing in the brain. And it is clear that LLMs have problems and abilities that humans don't. So we are seeing divergence already. One good example is hallucinations, which really resemble schizophrenia in humans, which is still quite rare, right? I mean, most normal people do not have or exhibit schizophrenic symptoms, but LLMs do hallucinate and seem to make up knowledge and do things that at least humans don't do unless they intend to. So we do have to be very careful, and so similar methodology does not imply similar architecture or findings for LLM. So it could be that we have a similar methodology for investigating AGI and consciousness, but the answers might surprise us. So we have to be open to answers that are not going to be perhaps what we would expect with humans. So we have to be prepared for surprises, but we still maintain that the methodology is going to be similar in investigating AGI and consciousness. So what could be such a methodology? This is a question, of course, that really consumes some of us, because we don't have the answer to this yet. And as I said, we really want to look to cognitive science for the answer. So I went back and looked at some cognitive science frameworks, trying to understand, which one do we really want to use for evaluative purposes? How can we think about LLMs from a large cognitive framework in a way? And one framework that we are inspired by, my students and I, is Fodor's theory of modularity. This is quite an old theory in a way. It came up in the early 1980s with Fodor's seminal book, but it continues to be influential. And the key idea, for those who are not too familiar with it, is exactly what it sounds like, that the cognitive, our cognition can be thought of as these informationally encapsulated modules. And here you have some examples from Fodor's books, and the page numbers also here. There's a spoken language module, there's a written language module, there's a visual object recognition module. These modules are informationally encapsulated, and they cannot they are self-contained in a way. And there's a lot of debate about how deep or shallow these modules go, and what these modules are. But the key, even in all of these variants of the theory, the premise really is that we can think about our cognition as a set of informationally encapsulated modules. And modules can interact as characters, massively modular architecture of the mind illustrates. So this is, sort of inspired by Fodor. It really builds on Fodor, but it offers both reductionist and non-reductionist methodologies for understanding mental processes. Now, what I mean by that is that we can study cognition and mental processes in a reductionist way, because each of these modules is informationally encapsulated. So we can study language comprehension or language production in a way, kind of isolated from the other modules. And indeed, this is what a lot of cognitive science research seems to have done. But there is also, I believe, looking at recent papers, growing recognition that we can take a complex systems approach, which is essentially non-reductionist, that can look at sets of interacting modules or even a massively modular architecture, rather than one module at a time. Because how do we study this interaction if we just take a reductionist approach? So I think that's quite exciting in a way, and there are new tools for doing that. And interestingly, in LLMs, we are starting to see this direction take hold as well. So we're already seeing modularity being implemented in advanced LLM-based architectures involving reasoning and communication. So here you have an example on the right-hand side. And as you can see from the authors on the left-hand side, what is really encouraging is that there are cognitive scientists and computer scientists who are typically involved in this work, which is really quite exciting and just what we need. And we see a kind of modular architecture, when you look at this agent architecture. Now, I should say a little bit about what the task over here is. And it, kind of in the title, you see that communicated, that they want to build an agent that cooperates with other agents in this environment to solve a task. And so the task is, let's say in a home environment, a simulated home environment, you're trying to do something that requires several agents coming together. So it needs some teamwork. One person cannot do it or cannot do it efficiently. And so can we get these embodied agents, to cooperate modularly, and communicate and reason and, do all of those things to solve this task effectively. And we're starting to see this modular architecture being applied. This was just published earlier this year. So it's already new. There aren't too many papers like it because it's complicated to build these modular agents that have several modules within them. But we're already starting to see this in implementation. However, we have not yet started to see modularity applied to understand language models. That what can language models do? What's the cognition behind language models? We're not seeing something like characters massively modular model, that for language models. So our hope is that that's coming in the next 1 year, because to us, it seems very evident that language models do have a modular structure. They are capable of different things, that are informationally encapsulated, but it may have a different structure compared to what we might expect in human beings. So we need to figure out what that structure is and evaluate hypotheses based on that. So I think that's work still needing to be done, that we are just starting on in a way in our group and also in other groups. So our claim is, and this is really just a claim, it's based on a belief in a way, but there's good evidence from other researchers and this kind of work that you just saw that this is possible. And the claim is we can model the cognitive abilities of an LLM as a network of interacting modules. So this, in a way, is a very simple structure. We believe it can be much more massive than this. So for example, even just a reasoning module, we think that there shouldn't just be one reasoning module. There are probably different kinds of reasoning that can go in, different kinds of planning, different types of communication. And as the language models get bigger and more complex, we think that we will start to see it reflected in the complexity of the modules and how they interact. So this is really rather simple in a way, right? Compared to what you see here for the human mind in a way. And even this is kind of argued to be a little bit simple for mapping the modular structure of the human mind. So we think that this is the beginning, but that to understand language models, we can have a much bigger modular network. And it's an open question what that network is, what it looks like, what's interacting with what is informationally encapsulated. So these are all open questions for understanding the large language model from a cognitive perspective. And the claim too is that a complex systems approach, so the non-reductionist approach, will really be needed to study this network and its emerging properties. So just like with cognitive science, even with LLMs, perhaps because it's so overwhelming in a way, we are seeing each module or the one ability at a time, such as the reasoning ability and so on. It's being evaluated in a reductionist fashion. We are exploring one module at a time, but we're not seeing something where all of them are being investigated together as a complex network. So both are compatible, both are equally valuable lines of research, but for the second one, we still haven't gotten started even, I would say. And complex system research is something that I am very passionate about. So some of my students do work on this, where we really do believe that for studying interesting phenomena, we cannot just take the reductionist approach. We do need to model interactions between simpler entities, and there are emergent consequences of such microscopic interactions that you can only really start to map if you look at the interactions and the entities and the system as a whole. If you just study one entity at a time, these emergent consequences will not reveal themselves. And so this is a long line of research, right, outside of AI. So in computational social sciences, we've seen this research with social networks for many, many years now. There's Conway's Game of Life. This is like 40, 50 years in the making. So there's a lot of precedent for doing this kind of work. But within AI and understanding the cognitive abilities of AI, we have not seen this kind of work fully emerge yet. And so I do think that we need to borrow some of the tools from this field to understand the network of interacting modules within that underpin the abilities of large language models. This is from our own work. This is from one of our own papers, where we also think that there's a entire new science around comprehensively evaluating AGI subproblems, such as common sense problem solving. And historically, even going back 2-3 years before the large language models, it was again very, very reductionist. So there would be a paper on multi-set question answering. There would be a paper on organization. And more recently, there would be a paper on theory of mind. But what we are arguing is that for this kind of reasoning, we need to again take a complex systems approach where you pose a problem to the machine, and then the machine gives solutions. And then what we believe is that there needs to be a human who then, almost like a Turing test architecture, kind of is in this open loop session where, based on the machine's answer, you then probe further, by sampling from one of these problem contexts and one of these 3 areas of common sense. And it's a circular open loop evaluation. It's almost like how a therapist, talks to a patient or a client, right? Where it's not just, you're not administering a survey, which is kind of how AI evaluations tend to look like. Instead, we're saying that the Turing test really is a very good model in a way, where you're trying to converse with the model, but you're not trying to convince anyone that the model is a human being. So that's the goal of the Turing test in a way. But we are still taking a protocol, but what we are really saying is that let's have a conversation with the model within bounds. So if you're evaluating common sense, then we need to ask the model common sense questions, and it needs to be pre-decided. We don't want to make crazy things up on the fly. But we do need this kind of template and evaluate different areas of common sense reasoning in one evaluation session. So that's kind of what we are really trying to get to, that instead of just evaluating one at a time, let's evaluate the whole thing. The different areas of common sense, the different modalities of common sense are all evaluated in one open loop session. And then we can kind of look at a chart like this to see, do we believe the machine has common sense? Why or why not? And is it able to do different types of common sense all at the same time? So that's kind of, and we think that this protocol can then be expanded even further to other AGI problems, to AGI as a whole, and hopefully to consciousness as a whole. So that's kind of where we are headed, but it's still very early work. So some open question of interest is, how correct is our assumption, first of all, that cognition and LLMs can be modeled using a modular theory? This is not, settled in a way that, the LLM can be thought of as a set of informationally encapsulated modules that interact with each other. This is, I don't think that anyone in the AI community believes this to be settled, and so this is kind of the question that really arises, that can that model really be applied to LLMs? And if we can, is there consensus on what these modules are, how they interact, and what their capabilities are in the independently developed LLMs currently in use? So what we mean by this is that there's not just one LLM. I think unlike the human brain, there are these different LLMs that are coming out, so whether it's Llama from Facebook, whether it's, obviously GPT 3.54, whether it's Bard from Google, and the Baidu has an LLM. I mean, all the big companies, Amazon is working on one, Apple is working on one. No one has tried those out, obviously, but it stands to reason. The Anthropic, which is kind of like a rival to OpenAI, has its LLM, and so on. So there are many LLMs that even in just this 1 year, everyone has leaped onto this bandwagon. All the big companies, small companies, startups, they're all working on LLMs. So I would submit that in less than a year, we're going to see probably like 20 LLMs that are like competitive. And they are not, we cannot think of them like 20 brains, that are of the same species. The architectures are going to be different. The number of parameters are going to be different. The data that they have been trained on will be very different. So it's quite possible that even if we can use a modular theory for modeling cognition in these LLMs, the actual architecture, modular architecture, the modules and the way in which they interact could be different from LLM to LLM. So we need a scientific way to figure out what the structure of modules is, what this network is, and how do we evaluate cognition in LLMs or compare cognition in LLMs using this kind of a theory. So it's more there are more degrees of freedom in doing that than when we do it with the human brain. And as LLMs get larger and more powerful, it can be systematically decompose this increase in cognitive ability. So we know LLMs are getting bigger, right? And so the question here is that how do we explain their increase in power from the modular theory standpoint? So there are three possibilities, right? So one is that there are more modules that are getting added, right, in a sense. So as the LLM is becoming more powerful, it's basically like more modules getting added. That's one possibility. A second possibility is that individual modules that already existed in the earlier LLMs are becoming better. So modules are becoming better. And then the third one is that there's densification of network connections. So if two modules that may not have been interacting properly in the past in service of a bigger problem are now able to share information because of the bigger LLM. So, and these two are not incompatible. It could be that all three of them most likely will happen as LLMs get better and more powerful and are trained in better ways. But again, how do we quantify, along these three dimensions, assuming that modularity holds? And can we describe phenomena like consciousness and sentience in LLMs as an emergent phenomenon of a complex network of interacting but individually self-contained modules? And how would we know? What would be independent test of consciousness in LLMs? The third question is obviously a very big question that I'm sure many people in this community are really interested in. we believe that consciousness in LLMs, if it ever comes around, will be an emergent phenomenon. Now, there's no like one module that says the LLM is conscious or not conscious. So we feel that the best way to understand it is as a complex network of interacting modules. But the how to actually do this and what the test is right now not something we have an answer to. So before I close, I just want to thank a lot of my acknowledge a lot of my collaborators and funders. So the projects that I spoke about at the beginning is takes a village to work on these projects, and I'm grateful to all of my collaborators who have kind of been with us on these projects. And with that, I'll close out. If you're more interested in the work we're doing, do connect with me on LinkedIn and also visit our group website, which is aicomplex.github.io. We have just launched this website about a month or two ago, but we are continuing to add stuff to it, add papers and projects and other things to it over the next 1 to 2 months. So do reach out to me and connect and visit our website if you're interested in the work that we're doing. And with that, I again apologize that I could not be there in person or live, but have a great symposium and glad that I could participate remotely. Thank you.